Okay, so I'm going to solve with you that problem 1.7 from Griffiths' book, third edition, which is a problem, is an example of the Ehrenfest theorem. So let me write here, Ehrenfest theorem. What this theorem says is that the expectation value of a quantity obeys classical mechanics. And this problem is to solve one of these examples. And what is this example? Is the derivative of momentum, but now the expectation value of momentum, because we are doing quantum mechanics. We want to show that this is equal to the derivative of the potential energy, but not just the derivative. We are thinking here about the expectation value. Okay, so that's what we want to do. Well, we already discussed in class how to compute the expectation value of momentum. Remember how we did? Was that sandwich of that operator moment, right? So this operator moment is h bar over I and the derivative in x, which is acting then on the wave function. Okay, so this was the expectation value of momentum going from minus infinity to infinity. Well, now we are going to do the derivative of that. All right, so the derivative of that, I'm going to put this derivative in time inside that integral, so it will become a partial derivative in time, acting on all those terms. And let's see now what we are going to do with all this. Well, first that h bar over I is a constant. I'm going to take it out of the integral. And then I'm going to do this derivative on each of these terms. So we'll have now an integral of two terms. No, the one is this derivative in time of the psi conjugate with the derivative of psi in x, plus the second order derivative where we now have t and x, and that's it. Okay, you see that there is always a minus infinity to infinity there. If I don't put it there, it's just because I'm lazy. Okay, all right. So this second order derivative here, it doesn't matter the order in which we do that. So we could write it like this. Let's first do the derivative in time. Okay, and why we are doing this? Because we are going to substitute this using Schrödinger's equation, and we are also going to substitute this using Schrödinger's equation. Well, what was Schrödinger's equation? Let's write it here on the corner. I h bar derivative in time of psi equals to minus h bar squared to m, second order derivative in x, potential energy, and the psi. Okay, now I'm going to isolate just this part here because that's what we wanted down here, right? So let's isolate that. We already did this in class. Let's do it once again. This will now become h bar, because I'm dividing by this h bar here. The I that would go in the denominator, I bring it up so it becomes a plus I divided by 2m. And on the other term, I'm bringing the I up so it becomes negative, and I have the potential divided by psi, divided by h bar and the psi. Okay, so this is what I'm going to use down below, and I'm going to also use the conjugate of all that. So let's write it here because we'll need it. Now where the I is, I get a minus I. Remember to put the star everywhere. Here becomes a plus I, and the star as well here. All right. So that's the one that we are going to need in this part. Okay, so let's then rewrite all that. So we have h bar over I. Very good. Now let's be patient to write all those terms. And so that integral, and let's go step by step. So this term here, I'm going to copy what I see there, minus I h bar over 2m, second derivative Then I have, well, and let's copy already that derivative in x. No, so this was my first term. We then also have plus IV over psi over h bar and the psi star with the derivative. Very good. So this is our first term. Now we're splitting two. How about the second term? Well, let's pick, we have this derivative in x, so let's put it here. And now let's put it everything that corresponds to this term here. So it's going to be IH bar over 2m with that second derivative in x. So, and then we have minus IV over h bar with the psi. And that's it. Okay, so we have four terms. And look, there is a derivative here that can perhaps give us even more terms. If I see that it applies here, there is a potential dependent on x, also the psi, so I will get two more terms. So I'll have 1, 2, 3, 4, 5 terms to play with. But we're going to see that some of them can cancel. So let's have a look at this part here. Okay. So the first term, I'm going to put this IH bar over 2m here. What this term gives us is a third order derivative. Very good. Now, how about the second term? In that second term, we have, let me put the constants out. We have psi of the derivative of b, psi, and we have psi b and the derivative of psi. Well, so you see that we can already identify something that we can cancel, which is this term here, which is plus, is positive, with this term here with the negative sign. Okay, okay. So well, I said 5 terms, but you see that what we really have is 1, 2, and 3 terms. And look at this one. This term here, very good. Let me isolate just this term here because it calls attention. This is the term that we really want. So let me isolate it here. Look, in front of this whole term, we have h bar over I. And this term in blue that I told you, let's isolate, there is a minus I over h bar. And this is inside the integral of this psi conjugate, the derivative, and the psi. Okay, so this is that blue term that I isolated here because it's the most interesting one. What do we have here? Well, the h bar cancels, the I cancels, but careful, there is a minus sign that remains. And what is this term in the integral? Is the sandwich. It's the sandwich of the derivative of the potential, which is, let's come up here, what we wanted. Okay, so this term that I isolated here in blue is exactly what we need. This term is equal to the expectation value of minus the derivative of the potential in x. Okay, so this is what we want. We got it. It's there. But there are 2 annoying terms still remaining in this story. What are these annoying terms? Let me put them with a different color in red. So it's this term here and that third order derivative term. Okay, so these are the extra terms that we'll have to play with. They are still remaining there. We'll have to play with and show that they cancel. Okay, and if they cancel, we are done. Okay, so let's pick these terms. Let's try to remember what they are. So we have that h bar over I. Both terms have this I h bar over 2m. One is negative and the other one is positive. So let me put this term here. IH bar over 2m. Then in the integral, the first term there is a minus, and then we have the second order derivative of the psi star, the conjugate, with the first derivative of psi, okay? And the third derivative that we have is this term here. Oops, third. So this is the one that I said is our annoying term that remained, in addition to the one that we really wanted to show Ehrenfest theorem. And what we need to do is now show that these two terms will cancel each other. How we're going to do this? By parts. Okay, so first let me get rid of this I already. Well, it doesn't matter, this is all constants anyway. What we really care about is what is inside this integral. So I'm going to do it by parts. You pick the term that you want. I'm going to start with this one. Okay, now remember how we do these integrals by parts. Now, so suppose we had here, I'm going to put up here, suppose we have this integral of f, two functions, f and g. How do we do it by parts? It becomes f and g minus, and then we switch the derivatives, right? We did this in class, we discussed it. This integral a to b, well, here we have a to b, here we have a to b. Okay, so who is playing the role of f in my case here is going to be that psi star, and who is playing the role of g is going to be the second order derivative. Okay, so doing by parts, I now have psi and that second derivative. And the minus sign, and now I switch those derivatives, so I get this derivative in the psi star. And here becomes the second order. All right, is made my g. So this is the derivative of my f, and this is what the whole thing was for the g. Okay, remember what we said in class? If the wave function is square integrable, which is what we want to be normalized, the wave functions have to go to 0 at infinity. So we got rid of this part. So the term that is surviving is this one. Well, what are we going to do with this one? Again, we are going to do things by part. And what is going to be the f now? That derivative, who is playing the role of the f is this derivative, and who is playing the role of our g now is that first derivative. Okay, okay, so let's go again by parts. Don't forget that there is a minus sign here. Okay, careful. So we have minus sign, and then we go f and g. Between minus infinity to infinity. And then minus with minus, we get plus. And in the integral, we have now the derivative of our f. And we have our g. Well, again, for these wave functions, which are of interest in quantum mechanics, not the ones that can be normalized, the derivative also goes to 0 and infinity. So what survived? This term here. And let's go up. You see that this term is the same one that we have up there with a minus sign. So we now see that this one and this one cancel. So finally, we got what we wanted. What is it that we wanted? To show that the derivative of the expectation value of momentum is indeed equal to this term here. All the others disappeared, which is the expectation value of the minus the derivative of the potential energy. So this is what we wanted to show, and we are done.